Alright, welcome to my channel. Today we're looking at the aggregated residual transformation for deep neural networks. So basically the paper that introduced the ResNeXt. The paper won secured second place in 2016 ImageNet classification task. So this paper is basically a combination of VGG, ResNet and Inception all together. All the reviews of this paper you can find on my channel. So if you haven't watched them already, go do it and we can dive into the ResNeXt paper. The main problem that they actually saw in ResNet is that when you basically only increase the depth of the network, so like ResNet or VGG, you reduce the free choice of hyperparameters because the only thing you can increase is basically depth, right? So depth is exposed as an essential dimension in neural network. And unlike VGGs, the family of Inception models have demonstrated that carefully designed topologies are able to achieve compelling accuracy with low complexity. So by stacking more layers, you increase the amount of computational power you need to use to train that model. The goal of the Inception was basically to reduce the complexity while still keep really good accuracy results. So in order to do it, they used a split transform merge strategy. So as you remember, we basically got the input, we branches out to 4 different convolutions, operations, and then at the end we will concatenate them. But the Inception had the one big flaw, and despite the good accuracy, filter numbers and sizes are tailored for each individual transformation, and the modules are customized stage by stage. It is in general unclear how to adapt the Inception architectures to new dataset and tasks. So that was the biggest problem of the Inception, because as you remember, VGG and ResNet can be easily adapted to different problems and could be used for transfer learning, right? But Inception couldn't. So what they present in this paper is simple architecture which adopts VGG and ResNet strategy of repeating layers while exploiting the split transform merge strategy in easy extensible way. So basically, if you see this image at the start, they convert the regular block into the kind of Inception block that the fullnet had. The results of ResNet are interesting. They trained 101 layer ResNeXt and it was able to achieve better accuracy than ResNet 200 with only 50% complex. So let's see what the ResNet is all about. As you can see, that's the architecture and it's pretty similar to regular ResNet, but we got this cardinality C parameter over there. So that's the residual block as we had before. So all of these 3 are the same, equivalent in terms of performance. So basically in the first case they created projections of the input. So as you can see, cardinality is the number of the branches we have in one block. Yeah, they create basically different projections, pretty much the same as they did in Inception, but they sum them at the end. In the version B, they concatenate them, but the most important is version C, because they actually used it in the final model, and they used something called as group convolution. So imagine we have 4 input channels and we got 8 output channels. So normally when we want to calculate the first output channel, we basically take a kernel and iterate over one feature map in the input, then second one, then third one, and the fourth one, and we sum it up. And that's how we got the first kernel, and we repeat it for each feature map. So when we got the group convolution, we actually, if we introduce group to 2, we basically output feature maps and input feature maps into 2 batches, let's say. So now we only calculate the feature map over there using only 2 kernels. We don't look at the other kernels. The same we do for this ones. They only see these 2 kernels, they don't see the other 2. And at the end, so basically if we want to calculate this one, we take the kernel from here, go through this one, iterate over the image, iterate over feature map here, and then iterate over the second one and sum it up. So we only use these 2. Alright, and at the end we concatenate them all. So the output size is pretty much the same as we did normal convolution without grouping. And as you can imagine, it really speeds up the computation significantly, and that's what they use here. And as you recall from the AlexNet paper, they actually use it. They use 2 pipelines to train the model, and it actually was related to limitation of GPU. But in this case, it's just basically faster than the B and A method. So what they do here is basically they add parameter called group and they set it to 32, so the cardinality value. Basically the whole architecture follows the ResNet, pretty much the same as it was before. The one thing is worth to keep in mind that when we downsample 56 to 28, the projections here, we don't need to manipulate any feature maps, which is better than the ResNet, as you can see. But we need to downsample the projection from here also by 2. So we use stride 2 in the first block in this convolution 3, and we need to downsample the residual connect. Okay, so and surprisingly both of these networks have pretty much the same number of parameters. And yeah, so they refer to C as cardinality, and they show that by experiments the cardinality is essential dimension and can be more effective than the dimension of the width and depth. Basically, by manipulating the cardinality, don't increase the computational power that we need to use to train model. So basically in this architecture, the essential dimension to increase the accuracy while keep the same complexity is cardinality. So they will actually play around with some of the values of the cardinality, and they used 32, and in this case the width of the bottleneck is 4 and the width of the group is 128, and it's only referred to convolution 2. So basically in this case the width of the bottleneck is 4. So how many feature maps we split into? So basically 120, and the whole bottleneck size is 128, and then by 8. So as I said, they train all 3 forms, B and C, and obtain the same results, but they choose to implement C because it's more succinct and faster than the other 2 forms. And that's what you're going to implement in PyTorch. So yeah, they use cardinality 32 and bottleneck with 4D. So basically 4D depends on which block we will use. Really important thing they point out at the end is the increasing cardinality shows better results than going deeper or wider. And they actually trained the model with residual and without residual connection. And without residual connections, the gap is much bigger. And what it says is basically that residual connections are helpful for optimization, so basically for the gradient flow, and aggregated transformations are creating a stronger representation. So basically by manipulating the cardinality we can achieve better results by getting a stronger feature extractions from the data we have. I think that's basically it. I'm just gonna quickly sum up, I think, the really important thing they say. So they model basically improve accuracy while maintaining the model complexity and number of parameters. So that was the main goal of this paper, and they basically wanted to minimize the modification of other hyperparameters. And I think with all that information we can jump into the Google Colab and start to code it. Alright, so first of all, I'm going to use the code from last video when we implemented ResNet, and we're going to basically slightly modify it. So starting with residual block, we pretty much get rid of most of it. Alright, and we also slightly modify the convolution block. So we add the group, which is equal to 1, and bias equal to false, because you actually don't need to use bias before the batch normalization. So group is equal to group and bias equal to bias. Alright, so that's basically it for convolution block, and now we can go into the residual block. So to start with, we're gonna pass also stride. First gonna stay, because first is a bit different. Cardinality is equal to 32. Alright, for simplification I'm gonna call it a C. We obviously got the rest channels, so the channels between the projection in the residual block, so like intermediate channels or so. So basically they're gonna be out channels divided by 2. So it's gonna be these channels over there, and they obviously are 256 divided by 2. Okay, so now we can define C1. So first convolution, so it's going to be ConvBlock, and we pass in channels, out channels, kernel size is 1, stride is 1, and padding is 0. So we keep the same dimensions, only reduce the output channels. Okay, so convolution 2, that's going to be the one where we perform a group convolution. So it's going to be ConvBlock. And now we got, oh, it should be res channels, sorry. Now we got the res channels. Res channels is an output. Kernel size 3, stride 1, padding 1. And group is cardinality, so C. And obviously stride is the one that we're going to pass. So as you remember, we downsample after every few blocks, right? And we downsample and increase the feature map. So then we need to use a stride 2 in 3 and 3 convolution to actually perform it. Alright, and we got C3, and we got a res channels as an input, and out channels as output channels 1, 1, 0. Okay. We obviously got the value, and forward. Okay, so again, the same convention and as it was in ResNet. So okay, so we get C2 and we pass F. We not pass it through value yet. Okay, so we got the input go through our 3 convolution, and we got H, which is basically added up F and X. So we got the identity operation. So we return H. So as I mentioned before, when we get the stride 2, we need to create a projection where we also downsample the projection from the block before. So how are we going to do it? We're going to introduce new variable. So it's going to be downsample. And we only downsample when the stride is 2, right? When we pass stride 2. So basically if stride is equal to 2, then we perform downsampling with, then we downsample the projection. So it's going to be a ConvBlock with, so in channels, out channels, kernel size is going to be 1, stride, we pass stride, so it's going to be 2, and padding 0. Alright. So if self downsample, we just pass X through projection. Okay, but we also have a 1 exception from this rule. So you get the first layer, first convolution, then we got max pooling, and our output is 64, right? So then we need to basically, because we get the residual connection from here, we need to add it up to the output of this, and to add this to this. So we got 56 and 56, so that's alright. So we don't need to downsample it. Yeah, but we still need to get from 64 feature maps to 256. So we need to create a projection shortcut just for the first block. Alright, so how we do it? We basically, so we also call it downsample or first. So first is true, we create this projection and we got our in channels and out channels. And in this case, we get a stride 1. So the in channel is going to be 64, out channel is going to be 256, so that's what we want. And the stride is going to be 1, so we ain't going to downsample it. So great. To be honest, that's pretty much it. We're just actually going to modify a bit architecture here. As you remember, that's the first block we add to the whole module list with blocks, and the input is 64, output 256, but we pass stride 1, and since it's a first block, we pass through. So in other residual blocks, we basically just need to add 2. So that's the first block, that's the first, as you can see, this is gonna be the first block out of 4, first block out of 6, and the first block out of 3. So what we do here, we pass stride 2 to get this shortcut connection downsample. And in the next ones, we pass stride 1. Alright, the rest is pretty much the same. I just added the initialization weight with k-min normal, so that's how they did it in the paper. And yeah, let's see if it's past the... Okay, alright, we should add groups. Yeah. Oh yeah, so it's produced the output that we want. And I actually recently saw the Torch summary, which is similar to TensorFlow. We can see if it's actually how it's actually look. To start with, we got our convolution batch norm, so basically the ConvBlock, and we got ReLU and max pooling. That's how the network starts, and we go through the whole. You can analyze it all, and at the end we got pretty much the same number of parameters that they claim in the paper. And yeah, that's it for this video. Hopefully you understand the ResNeXt better, and if you enjoy it, leave a like and hit the subscribe button, and yeah, see you in the next one.